Today about the categorification of the Lusztig-Vogan.
Great, thanks, Scott. And thanks for having me here. It's very early in the morning here in Sydney, Australia at 6 a.m. So I have to apologize. I'll surely be a little bit slow and sleepy for this talk. I just rolled out of bed, but it's really nice to be here. I was actually in University of Georgia physically just over 3 years ago now, right when I was finishing my PhD. So it's really nice to be able to come back 3 years later and tell you guys a little bit about what I'm thinking about. So this is a talk about some work in progress. Unfortunately, it's not done, so there's not anywhere you can read about it yet. And it's also a project that actually hasn't been on the forefront of my mind in the last few months because other things have been taking its place. But it's a project that I really like. And so I thought that it'd be a nice thing to talk about today. And what this project is it gives an algebraic categorification in terms of Soergel bimodules of a certain module over the Hecke algebra, which has significance in unitary representation theory of real Lie groups. So this is the context in which this project is. And what I want to do today is I want to tell you a little bit about my journey. So I want to tell you this story. I'll tell you about the background, how the object arises, and how I'm attempting to categorify it. So a little more precisely, this is my plan for the talk. I'll start out by setting the scene, and I actually can't see at all who's in the audience, and so I have no idea what any of your backgrounds are. So I'll spend some time talking about the story of unitary representation theory of real Lie groups. Perhaps this is something you're familiar with, perhaps you're not, but I'll start with this bit of the talk, and then I'll actually define the object that I'm thinking about, this Lusztig-Vogan module. And as I said, this is some geometrically defined module over the Hecke algebra that tells us something about the character theory of admissible representations of a real Lie group. And to define this module, I'm going to have to go into a little bit of geometry. So in the third part of the talk, I'll talk about a certain category of equivariant sheaves. And then finally, in the fourth bit of the talk, I'll describe an algebraic version of this category. So the categorification that I mentioned in terms of Soergel bimodules. And then finally, in the last bit, I'll put it all together. So feel free to interrupt me at any point in time. It seems that there are some people on Zoom and some people in the audience. I can hear the people in the audience pretty well. So if you guys just talk normally as you would in a seminar, I think I would hear your questions. And anyone in Zoom as well, feel free to interrupt me. Great. Okay, so here's the main character of today's talk, a real reductive Lie group. So if you are a person who likes definitions, then this is the set of fixed points in a complex connected reductive algebraic group under some anti-holomorphic involution. Or if you are a person who likes examples, you can think in terms of examples for essentially this whole talk. And you could think of one of these for examples. So a great one that maybe is your favorite real reductive Lie group, it's certainly mine, is SL2R, the set of 2 by 2 real valued entries with determinant 1. But for the purposes of today's talk, I'm actually going to keep a running example that is not SL2. Usually when I give talks, I keep running SL2 examples, but today I'm going to be brave and I'm going to give you a symplectic example as my running example. And part of this is because I'm trying to be brave, but actually more of it is because my categorification that I'm going to propose later has a few adjectives that I need to throw in front of real reductive group. And one of those adjectives is equivariantly simply connected. We'll talk more about what that means later, but SL2R doesn't satisfy this. And so SP22 is a nice example because it does satisfy all the conditions that I need to place. And so SP22, we'll be familiar with this. This is going to be the set of symplectic matrices, 4 by 4 symplectic matrices that preserve this additional Hermitian form, this diagonal matrix that I have written down here. And again, we'll remind ourselves about symplectic matrices a little bit later in case you don't think about type C so often. Or you could also think about SON as a great example of a real reductive Lie group, or UPQ, which is this set of P plus Q by P plus Q matrices that preserve a Hermitian form of signature PQ. So these are some good examples of real reductive Lie groups if you don't think about these so often. And the guiding philosophy behind today's talk is that we want to understand this real reductive Lie group by studying its unitary representation theory. So in other words, we want to study Hilbert spaces on which this group acts by unitary operators. And this philosophy fits into a much bigger picture that is it's certainly not a new philosophy, it's sort of an old philosophy that's sometimes referred to as Gelfand's program. And this is the idea that it's a common situation in math that we have a group acting on a topological space. and that we might want to use this to study the group. But the problem with this setup is that there's not much room for algebra. And so Gelfand proposed that we reduce this problem of studying a group acting on a topological space in 3 steps. The first step is to change the problem to study the group acting on functions on that topological space, because then that gives us the structure of a Hilbert space. And then the next step is to recast questions about that action of a group on a Hilbert space in terms of irreducible such actions. And then finally, the third step is to describe all irreducible unitary representations of this group. So this is kind of the underlying program that we're operating with. And if you haven't thought much about this world of unitary representation theory before, here's just a little bit of the history of how we can do this. So in the 1950s, Harishchandra realized something very important about this question, that we can recast it almost entirely algebraically. So at its face, this idea of studying unitary representations, groups acting on Hilbert spaces, is a somewhat analytic problem because Hilbert spaces are involved. But what Harishchandra realized is that we can change this into an entirely algebraic problem in the following way. So if we have a representation of our real reductive Lie group, we can always look for a maximal compact subgroup within our group, and then we can restrict our representation to the maximal compact subgroup, and we get a representation of a compact Lie group. And then another thing we can do is we can always differentiate our representation and get a representation of the corresponding Lie algebra, or if we like, we can get a representation, we can complexify and get a representation of the corresponding complexified Lie algebra on the same space. So starting with any representation, we can do this process and get some vector space that is simultaneously a representation for a complex Lie algebra and the complexification of a compact Lie group. And this process is useful because both of these objects, the complex Lie algebra and the compact Lie group, are things whose representation theory we understand better than the representation theory of some Lie group that's perhaps not compact. So this process moves us into 2 worlds that we understand better. But it's not entirely obvious why this process should work, because we're starting with some information about this representation of this big group, and we're changing it in 2 ways. So it seems like we should be losing a lot of information by transferring our problem into this different setting. But roughly, kind of philosophically, why this process still captures all the information about the original representation is because between the Lie algebra and the maximal compact subgroup, we gather all the information about the group. So the Lie algebra tells us infinitesimal information about the group. It tells us sort of what's happening around the identity, but it loses a lot of information. It loses information that distinguishes our original Lie group from coverings. But then if we also look at the action of a maximal compact subgroup, we have the property that at a Lie group, deformation retracts onto its maximal compact subgroup. So the compact subgroup captures all the fundamental group information, which is exactly what the action of the Lie algebra loses. And so if we keep track of these 2 pieces of information, it's somehow, I mean, there's a lot of theory that goes into this, but what Harishchandra showed is that this is enough to tell us about the original unitary representation. So this is kind of the first step if we want to understand unitary representations, is we can translate the problem into this algebraic world of studying GK modules. And then it turns out that this process that I just described has nothing to do with unitarity. I could do this for any representation of G. I could look at the corresponding GK module. But what happens if I start with a unitary representation is that the GK module I get is especially nice. So if we take a representation and restrict it to a maximal compact subgroup, then it's going to decompose into irreducible representations, into a direct sum of them, because this is a property of representations of compact Lie groups. So we know that our GK module is going to decompose into a direct sum of irreducible representations. But it's possible, if we started with an infinite dimensional representation of our real Lie group, that when we do this decomposition, one of the irreducible factors might show up infinitely many times. But what happens if we start with a unitary representation is this doesn't happen. So if we have a unitary representation and restrict it to maximal compact and look at the decomposition into irreducibles, each irreducible only shows up finitely many times. And this property is what's called admissibility. So unitary representations lead to admissible GK modules. And they're not the only representations that lead to admissible GK modules, but it is a property of them. So our strategy for studying unitary representations is to expand the class of representations we're studying slightly. And we will try to study unitary representations by instead studying admissible GK modules, and then eventually find within the admissible GK modules which ones came from unitary representations. So that's how I add my adjective admissible, which is going to show up throughout the talk. And this is basically what I just said. So since every unitary representation leads to an admissible GK module, we can start by studying these. And so this is the setting of today's talk. And a little more precisely, the setting we'll work in today is we'll fix some real reductive Lie group and within it a maximal compact subgroup. And then we'll complexify. So we'll lose the real structure pretty quickly. And throughout the talk, we'll be working with complex algebraic groups, G and K. So whenever I drop the subscript, I mean my groups are complex. And then I'll use Fraktur letters for the corresponding complexified Lie algebras. And so again, here's my favorite example that we'll be running with. So if we take SP22, this symplectic group that preserved the extra Hermitian form that I described earlier, if we want to find the maximal compact subgroup within this, it turns out it's two copies of SU2, which can be found one sort of in the middle and one at the corners, as I've written here. And then when we complexify, the complexified group corresponding to SP22 is just SP4. So the symplectic group 4x4 matrices. And when we complexify this maximal compact subgroup, we get two copies of SL2C, one living in the middle and one living in the corners. So this is our running example that we can keep in the back of our heads. And I'll just give a brief reminder before I keep going about symplectic vector spaces. And this is kind of more for me, I guess, than anybody else, because every time that I sit down and do this, I forget how these things work. So if it's been a little while since you've thought about type C, what exactly are these objects? So our group is the group of matrices, 4x4 complex valued matrices that preserve this symplectic form. So here's the form that we can apply to vectors in C4, and we ask for all the matrices that have the property that if we apply this form to two vectors, or if we apply this form to the matrix applied to those two vectors, we get the same thing. And this forms for us a group. And so then when we add the additional condition that we're thinking about this real Lie group, we want it to preserve both the symplectic form and a Hermitian form of signature 2-2. But we're not really going to think about the real group for the rest of the talk, so that doesn't matter as much. And then within a symplectic vector space, or within a vector space, we say that some subspace is isotropic if it has this quality. If the subspace, if we take the pairing, if we look at the set of all the vectors that pair to 0 with something in our subspace, this is W perp, and if the subspace has a property that it's contained in that, then we say that it's an isotropic subspace with respect to the symplectic form that we've chosen. And just a remark, since we're going to be talking about isotropic flags later on, all lines have this property of being isotropic, because what does it mean to be a line in this vector space? They're just all multiples of some vector. And then if we just plug in two different multiples of the same vector into our form, we can see that everything cancels out and we're left with 0. So this tells us that any line that we choose in the vector space is going to be an isotropic subspace. Okay. So that was a bit of a, oh, one more. Oh, here's the symplectic flag. So I'm actually not sure if this is standard terminology, but this is what I'm going to call it. Within this vector space, we're going to be thinking about flag varieties. So I'll call a symplectic flag one of this form. So a flag in C4 that has the property that we've chosen a symplectic line because all lines are, or isotropic line because all lines are isotropic. And then we've chosen this within some isotropic plane. And then within the perp space of the line. So a special flag of this form is a symplectic flag. Okay. And that was just a bit of a digression. So back to where we were before this. So I told you that we were interested in a certain class of representations, admissible GK modules. And it turns out that these have a nice classification. And the classification goes as follows. If we look at the action of our of the complexified maximal compact K on the flag variety of our group G mod B, it turns out that these form a Harish-Chandra pair in that K acts with finitely many orbits on the flag variety. And then we can classify all irreducible admissible GK modules with some fixed infinitesimal character in terms of irreducible K-equivariant local systems on those orbits. So the story feels somewhat familiar if you like thinking about category O and classifying irreducible modules in some block of category O in terms of B orbits on the flag variety. So this feels sort of similar, except that now our K orbits are slightly more complicated than B orbits. So in particular, they're not necessarily affine spaces. And they also don't necessarily have as nice of a combinatorial description in terms of the Bial group, but they are still geometric objects we can study. We can still study the action of this group on this variety and look at its orbits. And this classification can be realized very explicitly using valence and Bernstein localization. So in particular, we can look at the category of Harish-Chandra modules, which are these GK modules that have some fixed infinitesimal character. And valence and Bernstein localization gives us a functor, allows us to localize these and obtain certain D modules on the flag variety. And we get exactly the category of K equivariant D modules on G mod B. And the nice thing about valence and Bernstein localization is that it's not just an equivalence of categories, but we have functors in either direction that we can compute. So if you hand me some GK module, I can take its localization and I can find myself a D module. And if you hand me some K equivariant D module, I can take its global sections, and this will construct for me an admissible GK module. So we can use this to write down the classification somewhat explicitly if we work in the geometric category. So within this category of K equivariant D modules, we have certain standard and simple objects that are constructed as standard and simple objects usually are in these geometric categories. We have, if we take an irreducible K equivariant connection, if you like thinking about local systems, this is sort of the D module analog to a local system, on one of these orbits, and then push it forward under the inclusion map, then this builds for us some D module in this category. And it turns out that this D module, the standard module, has a unique irreducible quotient. And these irreducible quotients completely classify all of the simple objects in this equivariant D module category. And then we can just take this whole story and apply global sections, and we obtain two different classes of GK modules, these certain standard modules, which we get as global sections of the standard D modules, which also have an algebraic construction, but I personally prefer to think about them in terms of D modules. And then these have unique irreducible quotients, and this gives us the classification of all irreducible admissible GK modules. So I have some class of modules that I care about. I have a nice classification of these modules in terms of local systems on orbits. And to keep us grounded in reality, let's try to see what this looks like in terms of our symplectic example. Okay, so for our example of SP22, we can realize the flag variety as the set of all these symplectic flags. That's why I defined them. And again, this is true because of the same reasons why it's true if you're used to thinking about type A, where there's a natural action of the symplectic group on the set of all symplectic flags. And then you can take the stabilizer of the standard flag and see that it is the Borel. So this gives you an isomorphism between G mod B and this set of symplectic flags. And then the nice thing about this example is it's just small enough that I can attempt to draw things. So remember that a symplectic flag involves two choices. It involves the choice of a line, any line, and it involves the choice of an isotropic plane. So I can projectivize this whole situation to try to draw it, and I will draw and think instead in terms of CP3. And I'll draw my isotropic line as a point in CP3 and my isotropic plane as a line in CP3. And so this little caricature here is how I will draw a point in the flag variety. Okay. And then we have an action of this complexified maximal compact group on the flag variety. And this just acts as you would expect matrices to act on flags. And under this action, we want to look at orbits, because remember, I'm trying to sort of show you the classification of these representations, and it's in terms of orbits. So our first step is to try to find the orbits under this action. And to find these orbits, what I'm going to do is I'm going to look at what this action stabilizes and then see all the possibilities for how a generic flag could intersect with the stabilizer of this action. So you can see that this is naturally going to stabilize two planes in C4. our two copies of SL2 like this are going to stabilize the plane spanned by E1 and E4 and the plane spanned by E2 and E3. And again, since I'm drawing things in terms of CP3, I'm going to draw these two things as two non-intersecting projective lines in CP3. So P1 and P2. And now to visualize what the possible orbits are, we can think about options of how our flag could possibly intersect these two lines. So the first option, the generic option, is that our isotropic line doesn't intersect either of these other two lines at all. And so this is maybe a little bit hard to see, but there should be a gap between the black line and the yellow lines here. And this is sort of the open orbit. This is the most generic situation. And this orbit, it turns out, is 4-dimensional. So we can kind of count the dimensions by thinking about all of the possibilities. So we have 3 dimensions of choice now for where this point, which is secretly our line, lies in CP3. And then we have 2 dimensions of choice for where the line lies on the plane, I think. And then the fact that we have some symplectic condition cuts this down by 1 dimension. And so this orbit here is 4-dimensional. And then we can start degenerating and see what happened if we're not in the most generic case. So if we start to degenerate, we intersect we could have some situation where our plane intersects one of these 2 fixed planes. And this brings us to this next situation. It turns out that actually it's impossible to intersect just one of the planes because of the added symplectic condition. If we intersect one, then we need to intersect the other. And so the next most generate condition is exactly this, where our line doesn't lie on either of the planes, but the planes intersect both. And then finally, this could degenerate in either direction from here, where our choice of line is either on P2 or on P1. And we can't degenerate any further here because each of these planes themselves are not, this P1 and P2 are not isotropic. And so there are no flags where the line lies entirely on one of these. Okay, so this is sort of a caricature to try to visualize what's happening with these K orbits. And there are a few things to point out with it. One is that we have 2 closed orbits here, and each of these orbits looks like 2 copies of P1. We have 1 degree of intersection of where this point could possibly intersect P2, and then 1 P1's worth of what happens if we choose a point of intersection. We can see where this intersects the other plane P1. And maybe the thing to notice about this is that P1 cross P1 is also the flag variety of our group K. So this is not a coincidence. This is something that holds in general. So we have these 2 closed orbits. They have a nice property. And the reason why we're doing this is that we want to classify irreducible representations in terms of this geometry. But remember, there were 2 ingredients I told you for what our classification was. The first ingredient were the orbits. We had to look at the K orbits on the flag variety. And the second ingredient is that we needed to look at local systems on those orbits. So in this case, this is where that condition that I mentioned at the beginning of the talk comes up. It turns out that each of these orbits has the property that it only admits 1 K equivariant local system. And we can check this by computing the stabilizers. So the stabilizer of any point in the orbit, its component group tells us how many local systems are going to exist on that orbit. And this, at least in this example, this is something that you can sort of check by hand. You can write down what these stabilizers look like and convince yourself that they are all connected. So the only K equivariant local systems are the trivial ones. And this is exactly that equivariantly simply connected condition that I mentioned earlier. And that's why I chose this SP22 example, because it satisfies this condition. And what this tells us is that within this regular integral block of our category of admissible GK modules, there are exactly 4 irreducible modules, 1 corresponding to each of these orbits. And we could construct them again by taking a connection on each orbit, pushing it forward to build this irreducible D module and taking its global sections. Okay, so back to our general story after that side remark. So we have some category that we care about, or at least that I care about, some admissible representations. And a natural question to ask about it is about its character theory. So I've told you that it has a classification that's of the form standards. We have some collection of standards that have unique irreducible quotients, and all the simples appear in this way. And also this category is finite length, so all objects in the category have finite composition series. So it makes sense to ask about the multiplicity of some simple GK module in a standard GK module. These are kind of our favorite type questions to ask in representation theory. And so a little more precisely, we could look within the Grothendieck group of all of these admissible GK modules and ask about how we can express standard modules in terms of simples, what these multiplicities are. And this finally brings us to the title of the talk. The answer to this question is given in terms of this module over the Hecke algebra called the Lusztig-Vogan module. Okay, and so this brings us to the next section of the talk. But are there any questions about this first bit?
Yeah, I have a question.
Yeah.
So are you fixing a regular integral infinitesimal character, or
Yeah.
are you sort of with any infinitesimal character?
Sorry, what was the last part of the question?
Can you do this kind of a thing with any infinitesimal character, or does it have to be a special one?
So I'm fixing a regular one, but I think that you could, the singular case is also figured out. So so the whole thing is known, but I think that the definition I'm going to give you in a minute of the Lusztig-Vogan module is the definition if I choose a regular infinitesimal character. But the story is totally answered. So with a few modifications, we could do this for any infinitesimal character. Thanks for the question. It's so funny. I have absolutely no idea who you are or where you spoke from. I just see a tiny little screen. With some people.
Scott.
Oh, it was Scott. Okay, great. Any other questions? Okay, I will persist. So what is this module then that's supposed to answer this multiplicity question for us? Well, here's how it's constructed. So associated to the three things we've chosen, the complex Lie algebra and our group K, we can also choose Borel. And associated to this, we get the corresponding Weil group and set of simple reflections since we've chosen a Borel, and this builds for us a Coxeter system. And then the extra information that we get by our maximal compact is we get a reflection subgroup of our Weil group. Because K is itself a Lie group, and so we can take its associated Weil group, and it turns out that this is going to appear as a subgroup of the Weil group of the Lie algebra G. And it's of note, we'll see this in an example in a minute, but it's of note that this is a reflection subgroup and not necessarily a parabolic subgroup. So it's not necessarily true that this is generated by simple reflections. And associated to all of this, we have a Hecke algebra of this Coxeter system. And just to set my notation straight, I'll tell you exactly what I mean by Hecke algebra. So for me, a Hecke algebra is an associative V inverse algebra with a set of generators that are parameterized by elements of S, subject to a quadratic relation and a braid relation. And I will denote the Kasdagh-Lusztig basis within this Hecke algebra by B's. So for me, the deltas are the standard basis, and the Kasdagh-Lusztig basis is given by B's. Okay, so for example, in our running examples, we take SP22. This is type C2. So the Weil group is just generated by two reflections, S alpha and S beta. Here's a picture of the root system. And our subgroup, WK, so we know, remember that K looks like two copies of SL2. So its Weil group's going to look like the product of two Z2s. And so this tells us that we need to take has to be reflection through two roots that are orthogonal. So this Weil group is generated by reflection through these two roots, S alpha and 2 beta plus alpha. And so this is S alpha or S beta, S alpha, S beta. And so in particular, this is a reflection subgroup. It's not parabolic. It's not generated by simple reflections. And then if we look at the quotient of W by WK, it's just of note that this is size 2 in this example, and 2 is also the number of closed orbits. Again, this is not a coincidence. Okay, so how is this module defined? Well, the idea is to imitate Cauchy-Lusztig theory. So here I'll tell you the construction of the Lusztig-Vogan module. And if you're familiar with Cauchy-Lusztig theory and you like thinking about that, on the right, I'll sort of give you in blue the things that you should think about, that these various pieces of the construction should correspond to. So what we want to do is construct some module for the Hecke algebra. And this module is supposed to tell us something about the character theory of representations, of a certain class of representations. And so here's how we'll build it. So we start with some set, which is going to parameterize a basis for our module. And this is the set, the same thing that parameterizes our irreducible representations. So if we take pairs of a K orbit and a K equivariant irreducible local system, this is going to be our parameterizing set. And we should think about this as playing the same role as the Weil group in classical Cauchy-Lusztig theory, which also gives us a parameterizing set for the basis of the Hecke algebra. And then the next ingredient we need to do Cauchy-Lusztig theory is we need some sort of length function. So in the classical setting, length is given in terms of the element of the Weil group, but also if we turn to geometry, we know that the dimension of a Bruhat cell is given by the length of the element parameterizing that Bruhat cell. And so since we don't have a nice combinatorial description of our parameterizing set D, we can instead take length to be defined as its dimension. So the length of an element in the set is just going to be the dimension of the corresponding orbit. Okay, and then we build a free ZVV inverse module with a basis given by this parameterizing set. And this is analogous to just thinking about the Hecke algebra kind of in its simplest form. Before giving it a multiplication, we can always think of, we can think about the Hecke algebra as being a free module over ZVV inverse. It's parameterized by W. And then what we need to do is we need to give this, this module an action of the Hecke algebra, the structure of a right H module. And this should play some analogous role to the Hecke algebra acting on itself by right multiplication. Now, this is a bit of a black box for now because I need to tell you a little more about geometry before I can describe for you what this action is. But we'll see later that this can be constructed. And then what are the last ingredients that we need? Well, we need some sort of partial order on our set that corresponds to the Bruhat order. And this set here is a little bit more complicated because we have these local systems and orbits, but this partial order can be constructed. And I won't write it down precisely, but it's essentially the closure order on the orbits, except that now we're thinking about orbits and local systems. And so we have to be a little bit subtle about what happens in this order when we have different local systems on the orbits. But in our case, where we only have one local system on each orbit, then this can just be the closure relation on orbits. And then the last ingredient is we need something to play the role of the Cauchy-Lusztig involution. And it turns out that there is an involution on our module satisfying appropriate properties.
Is the local system closure order involved related to whether the local system on the extends to the closure? To extend and then on the closure is this smaller local system? Is that the condition? Yeah,
there's sort of, it gets quite specific. So it's about when it extends, but also it breaks into cases. There's sort of only certain ways that it can extend. And then each of these cases is described kind of systematically. But it's really, yeah, it's not something that's sort of nice and easily stated, unfortunately. Okay. So I haven't actually told you how this module is defined yet, because the most important bit, how it's actually a module for the Hecke algebra, I've kind of brushed under the rug, but we'll get to that in a minute. And so if you believe that there exists this module, then the big theorem of Lusztig and Vogan is that this module exactly answers our multiplicity question. So for every choice of element in our parameterizing set, there's some unique self-dual element. So that if we express the self-dual element in terms of our standard basis, this is given in terms of some collection of polynomials. And these polynomials are what are called the Cauchy-Lusztig-Vogan polynomials. And the punchline is that these polynomials determine the multiplicities of irreducible modules and standard modules. So by imitating, so we can sort of imitate Cauchy-Lusztig theory in a way that answers the multiplicity question for us. Okay. But I haven't, this is probably not so satisfying because I still haven't told you exactly how this module is defined. So this is our next section. To do this, we need to work with a little more geometry. So the first step is that we need a geometric upgrade of the Hecke algebra, and this can be found within the equivariant derived category of B equivariant sheaves on G mod B, or because later we're going to be thinking about Soergel bimodules, sometimes it's nice to think about this as the B cross B equivariant sheaves on G instead. And so perhaps this is a thing you're used to thinking about, perhaps it's not, but if it's not, these are sort of the main facts that you should know about it. The first is that this is a monoidal category under convolution. There's a way we can define convolution of equivariant sheaves. And it contains all the IC sheaves, which are parameterized by elements of W. These are the B equivariant intersection cohomology sheaves of the Schubert varieties, closures of the Bruhat cells. And so we can define within this derived category, the geometric Hecke category. And so I'm just going to take this to be the category that's generated by these IC sheaves under taking direct sums and grading shifts. So when we do this, we construct, there are different ways to construct this, by the way. This is just one of them. But this builds for us a monoidal category under convolution. And this category has a property that it's a categorification of the Hecke algebra. So this is not an abelian category, but it is an additive category. So we can take its split growth and degroup. And when we do this, there's a way to give it, since we started with a monoidal category, its split growth and degroup naturally has the structure of an algebra. And we can upgrade this to an algebra over Z V V inverse by asking that V act on the class of some sheaf as a shift by one. And this gives for us the structure of a Z V V inverse algebra. And it turns out that this algebra is isomorphic to the Hecke algebra. And so that's our first ingredient that we need. And we can play the same sort of game for the Lusztig-Vogan module. So remember, for us right now, all the Lusztig-Vogan module is a Z V V inverse module that's parameterized by some set. But we can find a categorification of this as follows. So instead of taking the category of B equivariant sheaves, we can look at the category of K equivariant sheaves on G mod B, which again, we're later going to think about as K cross B equivariant sheaves on G. And within this, we also have IC sheaves, but now our IC sheaves are constructed from a local system and an orbit. So we can take the intermediate extension of this local system and shift it appropriately, and this builds for us an IC sheaf in our category. But the nice thing about this setup is that because of the convolution formalism that exists in the B equivariant derived category, we naturally have a right action of B equivariant sheaves on these K equivariant sheaves. So, and this is just an action given by convolution. And so in particular, we have an action of the Hecke category. And so then we can define a category within this K equivariant derived category, which is just the category we get if we take all of the ICs and start convolving with everything in the geometric Hecke algebra. So we're taking the ICs corresponding to closed orbits. And then we can take the category generated by this that's closed under direct sums, direct summands, and grading shifts. And this category is sort of exactly the geometric version of the combinatorial object that we defined earlier. So again, we can take its split growth and degroup. And in this case, it's not a monoidal category. And so it doesn't have the structure of an algebra when we take the split growth and degroup, but we can still give it the structure of a Z V V inverse module in the same way we did before by asking that V just act by a grading shift. And then this is just some Z V V inverse module that has a basis given by IC sheaves that's parameterized by the set that we care about. And so we can identify it as a Z V V inverse module with the thing that we defined earlier, just because they have a basis parameterized by the same thing. But the benefit of doing this is that now we have more structure and we can use this to actually define the action of the Hecke algebra. So if we take stock of, Yeah.
So I mean, we need the split growth and decouple. It's an additive category, but not a abelian one. So you don't have exact sequences, I guess. So you're taking. So you just say what the split growth and decouple is. Then
Yeah. So I just want to impose the condition that if two objects, if I can write something as the direct sum of two other things, then that's what gives me a relation in the split growth and decouple, since we have no exact sequences.
I see, but then so if you have something like irreducibles, but it didn't split, irreducible in the standard say it didn't split, then what happens? How should I think of that in that case? Because if I don't have an exact sequence.
Yes. So actually, so maybe indecomposable would be the correct word here. So we can't. Yeah. So did I say irreducible anyway?
No,
yeah, so
I'm
should
asking. Suppose like you had I mean, I don't quite know how to think about this. Like you had I mean, if you had some. If you had something like in irreducible, some one module sitting inside another, but you can't split it, then they're just totally distinct objects in that sense.
Yeah, that's true. So it's kind of a not, so it's a different type object than a growth and decouple of an abelian category. It's sort of a more rudimentary object in some sense, but it is still a thing that we can define. So yeah, it doesn't distinguish as much between objects, like because exactly like you say, we could have some object sitting inside another object, but if we can't write one as the direct sum of the other plus something else, then their classes in the growth and decouple have no relation.
Okay, thank you.
Yeah, so it's maybe it's a rougher kind of measurement than we're used to if we're used to thinking about growth and decouplers of abelian categories.
Yeah, it's just I'm so much more familiar with the regular growth that I.
Yeah, me too. But it's like surprisingly, it's kind of enough. It's still like, at least in the classical setting, is the B equivariant sheaves, and in that case, taking the split growth and decouple still is enough that we can I guess it's so maybe we'll go. Actually, maybe that's a good thing to say. So let's go back to this for a second. So in this setup, so I've defined this category as taking these IC sheaves and taking the category generated by them. But another thing I could do is I could take the category generated by just constant sheaves on parabolics. So like if I take some standard parabolic PS mod B, and I just take constant sheaves on that, and then take the category generated by convolution of those constant sheaves, that thing builds for me the same category as this. And then what you can show is that, so every object in the category is going to be, you hand me an element of the Weil group, or some expression of it, so some just list of simple reflections. And from this, I can just take the convolution of all of those constant sheaves corresponding to those simple elements. And then this object, so this is some sheaf on G mod B, and I can realize this as the push forward of some constant sheaf on some bigger variety, a Bott-Samuelson variety. And then because of the decomposition theorem, this thing's going to decompose into the direct sum of IC sheaves. And so every object in the category does decompose into the direct sum. So that's why I have decomposition theorem written here, that kind of the reason why it's enough to just take this split growth and decouple is because this category is actually somewhat simple. Like everything in the category is just a direct sum of IC sheaves, which we think about as our irreducible objects. And so by taking the split growth and decouple, we really are, like, there's nothing more subtle going on where we have some interesting object contained as a sub-object of something else. Really, everything decomposes into the direct sum of the things that we care about. So it's sort of semi-simple in that sense.
But somehow it's like, but that's somehow related to like perverse sheaves, like everything decomposed. The category, this abelian category sitting inside here, somehow this category of perverse sheaves. I mean, somehow. So but anyway, I don't want to derail this too much, but with stuff I don't really understand. But it's somehow it's like there is some kind of abelian category in there, which is the category of perverse sheaves.
Yeah.
In the other case, is there some kind of abelian category hidden in there, like these K equivariant perverse sheaves?
Yeah, there are. I mean, you could take K equivariant, like you could come up with some. So these guys are the simple objects in the category of K equivariant perverse sheaves. But I sort of want to do, and I kind of need to know this information like in the back of your head, But for this actual construction, I don't need that extra structure of being an abelian category. All I want is just to take something more simple, this category that I get from taking my irreducible objects and closing them under direct sums and summands. So it's kind of something that's like a little bit more naive in some sense, but it's enough for our purposes.
Okay, thanks.
Okay, but wait, so there is an abelian categorification of this Lusztig-Vogan module.
Oh, so that I'm not sure of. So I don't think it's true that if we took the category of K equivariant perverse sheaves, that this would give the Lusztig-Vogan module as its growth and decroup.
Okay.
So yeah, I'm not sure if that would work. Yeah, I'm hesitant towards that. Like we can find a lot of the objects in this category within that category, but I don't think that it's exactly that it would give exactly the structure that we need. Okay, maybe I will continue. So this category is maybe defined in a somewhat mysterious way, but it is kind of explicit, and it is like, I think, the sort of a naive way to define it, perhaps. But what we're doing is we're just exactly trying to kind of imitate the structure that we have at a combinatorial level categorically, without imposing too much structure. And so by doing this, what we've done is we've just constructed some category whose split growth and decroup gives us this thing that we've defined so far as the Lusztig-Vogan module. But the benefit of doing this is that now we naturally have an action of the B equivariant category, which gives us an action of the geometric Hecke category on these sheaves that we've defined in terms of convolution. So when we take the growth and decroups, we not only get a ZV inverse module, but we also get the structure of a module of the Hecke algebra. And this can be taken to be the definition of the Lusztig-Vogan module. It's of note that this is in different language than the original papers by Lusztig-Vogan when they define this. So this is equivalent, but a somewhat different. Like if you read the paper, it won't be exactly in terms of this language. And so the point here is that this finally finishes the definition that I started a few slides ago, that if we take some element of MLV, which we can think about as the class of some sheaf, and we want to act by the Cauchy-Lustig basis element, this is the same as convolving with the corresponding IC sheaf and then taking the class. Okay, so one last thing that how am I doing for time? Oh, I'm not doing great for time. Okay, I think I need to, okay, I'm gonna skip these next few slides because I'm going I gotta get to the Soergel bimodules. So the last thing I was gonna say here is that this action, so I've defined for an action in terms of convolving with an IC sheaf. In practice, this is maybe not the easiest construction to do. And so this slide is just saying that there's another way that we can realize this. So convolving with an IC sheaf is sort of the same as pushing and pulling under this projection from G mod B to G mod PS for some standard parabolic. And this is just sort of a useful fact in computations. And the reason why I had included this fact here was because I was going to show you an example of the symplectic group, but probably actually I don't have time for this. But if you want to play around on your own and you're into this type C example that I've been giving you, you can take this construction, pushing and pulling, and you can actually apply this in examples. And so we can compute this Lusztig-Vogan action by looking, I'll just sort of show the slide quickly and then move on. But by using proper base change and sort of computing some fibers, you can look at what happens when you push and pull various constant sheaves in this SP22 example, and you can compute these actual polynomials. So by doing some geometric computations, we can compute one of these Cauchy-Lustig-Vogan polynomials in this way. So if you want to take a look at this slide later and play with it. But for now, the point of this talk was that we were supposed to try to do this algebraically. So we can reformulate this geometric definition in order to place it in the world of Soergel bimodules. And so this is where I need to start making a bunch of assumptions on my Lie group. So the first assumption I'm going to make is that my Lie group is equal rank. And so this means that both the complex group G and the maximal compact, the complexified maximal compact, share a maximal torus. And I'll let T be the Lie algebra of that torus. And then once I have this set up, I can look at the symmetric algebra on T star, and this has a natural action of the Weil group. And since it has a natural action of the Weil group, it has a natural action of this subgroup, which is determined by K, and I can take the invariance under that subgroup, and that builds for me a ring. I'll call that ring RK and the original ring R. And so, for example, in SP22, our ring is just going to be generated. It's a polynomial ring in two variables, alpha and beta, and the invariants are just the polynomials that are invariant under these two reflections that generated this smaller Weil group. And then with this setup, we can think about Soergel bimodules. So we can take within the category of RR bimodules, we can build what's called a Bott-Samuelson bimodule. And I realize that if this isn't in a world that you think about, this is somewhat quick, but this is some way that we can take some expression for an element of the Weil group and construct an RR bimodule called a Bott-Samuelson bimodule by just kind of taking tensor products over these invariants like this. And these things build for us a category of Soergel bimodules, which is a category we get just by taking these objects defined in terms of tensor products and taking the category, the smallest subcategory that's closed under direct sums, direct summons, and grading shifts. And then this is a category that categorifies the Hecke algebra as well, but it does so algebraically. So again, this is a category that, like our geometric category, is not abelian, it's additive. So we can take its split growth and group, and its split growth and group has the structure, or this is a monodal category, but under tensor products. And so its split growth and group has the structure of an algebra, and again, it's the structure of a Hecke algebra. So this is kind of the background of Soergel bimodules. And we can kind of imitate the geometric construction we just saw in this algebraic land. So we can construct an algebraic version of this geometric Lusztig-Vogan category. And the way we do it is as follows. Starting with a minimal coset representative of the quotient of our Weil group by its reflection subgroup, we can define a special RKR bimodule. So now we're thinking within the category of RKR bimodules instead of RR bimodules. And we define this module as follows. So we take something that just looks like R as a vector space, but we ask that the action of RK and R is that an element of RK just acts on the left by left multiplication, and the element of R acts on the right, but it acts in a twisted way by X. So first we take the element of the Weil group, which has an action on R itself, we twist by that, and then we multiply. And these we'll sort of call standard modules. And then we can define a category. And this is a category whose objects are RKR bimodules. And it's defined as follows. We take all of the standard modules, and then we just act on these standard modules by the Bott-Samuelsons, which live in our category of Soergel bimodules. And then again, we close under direct sums, summons, and shifts. And this category is sort of exactly analogous to the definition, the geometric definition we had of the Lusztig-Vogan category, where before we were taking our ICs corresponding to closed orbits, and we were convolving with elements of the geometric Hecke category. Now we're taking standard modules, which correspond to minimal coset representatives, and we're tensoring with generators of the algebraic version of the Hecke category. And because of this construction, this thing naturally comes with a right action of the category of Soergel bimodules. And it has a property that if we take its split growth and group, then we end up, so this tells us that we end up with the right H module when we take the split growth and group. And just a quick remark about these guys is that this construction suddenly, it doesn't really see the real Lie group very much. The only way that the Lie group contributed to this construction is it gave us the ring RK. But we could define this and this was really just defined in terms of this reflection subgroup of the Weil group. So this category makes sense for any reflection subgroup of the Weil group. And in general, there's not much that's known about these categories of Soergel bimodules. For example, it's not known if they have finitely many indecomposable objects or if there's any sort of combinatorial description of their growth and group. And so one sort of consequence of this project is that for certain reflection subgroups of the Weil group, this would give us kind of a geometric understanding of what these categories look like. It would tell us that they have finitely many indecomposable objects, for example. Okay, so now we're getting close, so let's put it together. We're almost to the punchline here. So where the stories come so far is that we started with some module for the Hecke algebra, which we care about because it tells us about the character theory of representations of a real group. This was MLB. And the way that we defined it was as the growth entity group of some geometric category of sheaves. And then there's also an algebraic category, which has the same, whose growth entity group also has the structure of an H module. And so the hope for this project is that this algebraic category in terms of Soergel bimodules gives us another categorification of the Lusztig-Vogan module, but something that's defined algebraically instead of geometrically. And so what's the point of this? Why would this be interesting? Well, one perspective is that this proof, which is essentially the Cauchy-Lustig conjectures, but for real groups. This proof is currently only done in a geometric setting. And so this could provide an algebraic world to establish these character theory type questions. So that's one thing that could be interesting. Another perspective is that these module categories that I mentioned are sort of independent interest if you're a person who likes Soergel bimodules. Module categories over Soergel bimodules are a thing that people study and are interested in. And this is some class of them that's not well understood. And in certain cases, when our reflection subgroup corresponds to a real Lie group, this gives us a description of these module categories geometrically. And then it also just kind of gives us a new toolbox for studying real groups, Soergel bimodules. But then the real reason why I sort of started thinking about this project was that there's this conjecture of Soergel about this Lusztig-Vogan module. The polynomials that appear in this module, they exhibit some sort of duality. And this is kind of analogous to the duality present in Cauchy-Lustig polynomials, but it's a little bit more subtle. For example, it interchanges different real forms of the same complex group. And Soergel conjectured that this character duality happening on the level of polynomials is actually a shadow of some categorical duality. Causal duality is what he conjectured. And so this algebraic setting might be a setting, like a different setting where we could sort of try to tackle this conjecture. But that's very kind of long term. I don't really actually have any ideas for how to do that yet. But that was sort of the motivation. So this is just my last slide now, which I seem to have 1 minute, so maybe I'll end on time. And this is how we can put it all together. So there's this geometric category that we define in terms of sheaves, and there's a way to go between the geometric category and my algebraic category of bimodules, and this is equivariant hypercohomology. So we have a functor from the geometric world to the algebraic world, and this functor intertwines the two actions. So in the geometric world, we have an action of the geometric Hecke category. In the algebraic world, we have an action of Soergel bimodules, and this functor intertwines those actions. Moreover, it sends, each of our categories has some set of generating objects, and it sends generating objects to generating objects. And so the last step is just to show that this functor is fully faithful on this geometric category. And if this is true, then it will establish that it's an equivalence of categories. And then because we defined the Lusztig-Vogan module in terms of this geometric category, this will establish for us that this algebraic category is also a categorification. So that's the goal. And then just one last remark is that this is all, it's not actually a special case, that's a little bit wrong, but it's closely related to this work by Bezrikov-Volonin, where they also provide a categorification of the Lusztig-Vogan module, but their setting is slightly different. They work with different adjectives in front of their Lie groups. They work with quasi-split groups, and their categorification has this same goal of trying to provide a proof of Soergel's conjecture, and they do so in a special case with somewhat similar type methods. And that's all. So I'll stop here. Thank you. Sorry, I kind of steamrolled the last bit. Are there any questions?
I have a question.
Yeah.
Hey, Anna, how are you?
Hi, Laura. I didn't see you until right now. I finally put the faces on my screen.
So maybe you could say a couple of words about the final step, like what's the hindrance there?
Yeah, in terms of showing that it's fully faithful. I mean, I think the main hindrance is sort of me understanding the setup more, honestly. So I've just sort of been slowly working on this. And yeah, I think that it should be relatively straightforward once everything kind of is stated in the right way. But the main hindrance is just kind of understanding how to work a little bit better with these categories of equivariant sheets.
Okay, cool.
I don't think it's particularly difficult is what I meant to say. It's not like there's a huge obstacle in building like a stumbling block.
So I have a question too. Is that Rx there? I think I missed it. Is that actually like this?
So the Rx
would that correspond to like an equivariant intersection cohomology of a Schubert variety, or is that?
No. So
how it's corresponding to a K orbit.
Yeah, so this corresponds, so if we take the closed orbits, so only this category is just generated by the minimal coset representatives. And remember that our geometric category was just generated by the IC sheaves on closed orbits. And so actually in that case, we could just take them to be constant sheaves on closed orbits. And that's what this corresponds to.
But so it sort of looks, isn't Rx coming from like a Schubert variety, or is it? Am I not understanding that?
Oh, maybe the notation's a little bit confusing. So this is corresponding to K orbits. So it corresponds to kind of the analogy, if we were looking at Schubert varieties, would be the single point Schubert variety, which is not so interesting. So these are just the like in the K orbit setting, we have multiple closed orbits, and the number of closed orbits we have is exactly the same as the size of this quotient of the Weil group by the reflection subgroup, and then if we take the constant sheaf on each of those closed orbits and apply hypercohomology, we exactly get these standard RKR bimodules. Is that what you're asking?
Yeah. So one other thing is that so I guess for Schubert varieties, for the closed orbit, so does all this make sense? Like if you replace the real group with the complex group to sort of recover the Soergel bimodule picture?
Yeah. So in that case, so in that case, if you took just like the single point orbit, which has a very boring, and then I guess took the constant sheaf on that, so the very boring sheaf, and then you applied hypercohomology, you would get, so you could define this Rx exact. I think what you're saying is that we don't have to have RK here, right? Like we could just define, this definition makes sense to define an R bimodule as well. And these are standard bimodules in this category, but these things don't. So for everything except the identity, these things don't actually live in the category of Soergel bimodules. So yeah, so it's not quite, there's not quite an exact analogy there, because if we like try to replace K with B, everything like all of this category is built from closed things. So we kind of take the stuff on the closed orbits and build upwards. And in that setting, there's only one closed orbit. So our construction of the Soergel bimodules is slightly different.
But in this study, you said this irreducible objects in your category correspond to the irreducible objects in the geometric category. So somehow you're able to see the local systems in your algebraic picture, I guess.
Mm-hmm. Well, the generating objects is what I said, yeah.
But,
so,
it's only the generating objects. I see.
Yeah,
so you don't. I see. So it's the generating objects. I see. So okay. So it's a little mysterious, I guess. I see.
And they're just generated by these closed guys.
Is there any kind of can you do a small example, or is it too complicated to do small examples? Even like in this SP22 case, could you check that it worked in that case, or is it too too complicated.
It can work in that case. And you could even do an SL2 example, actually, which is a lot simpler. The main difference is that, so this is the step where you have to impose the equivariantly simply connected condition, because this category, the algebraic category, only, it can't distinguish any non-trivial local systems, essentially. So we can think about these RXs as sort of, these are like the, in some sense, they're kind of like the local systems on the closed orbits, and we can build the rest of them in this way. But if we did this with SL2, we could define our geometric category. And if we just sort of forgot, so in SL2, we can think about the flag variety as a copy of the sphere, and then the orbits are the North Pole, South Pole, and a copy of C star. And so on the open orbit C star, we have two local systems. We have one trivial and one sort of Mobius local system. And if we just forget about the non-trivial local system and just think about the block of SL2R, where we only have local systems for each of the single point orbits and the trivial one on the open orbit, then we could do this exact same procedure there, and we could look at this corresponding category, and that should give us an equivalence between those two categories. And that's a case where like this could be worked out quite explicitly, and it should be pretty straightforward.
Okay, thank you.
Yeah, so the subtlety of this Soergel bimodule world is that it doesn't, I mean, it doesn't see the bit of the real group story, which is actually kind of complicated, which is the fact that we could have multiple local systems on orbits. That bit can't be captured in this like kind of algebraic combinatorial way, because the whole way that these categories are defined is just in terms of the Weil group. It doesn't have any more information.
Other questions for Anna? Okay, let's thank the speaker again.
Thanks for your talk, Anna. I really enjoyed it.
Thanks for coming, everybody.
Yeah, thanks for getting up early for us. I enjoyed it too.
Oh, you're welcome. Now I can have breakfast.
Very interesting talk. I'm Bill Graham, by the way, so you can't see me, but I can see you. So anyway, I enjoyed it. Thank you.
Thank you.